All right, welcome everyone. I'm going to go over some of the core expressions in this micro paper, and hopefully that'll help you understand some of the math and science behind it at a more intuitive or conceptual level, in case that isn't apparent right away. So if you're not doing research on a regular basis, or this just isn't your domain, sometimes it's nice to kind of peel back the layers a bit and see things from an intuitive perspective so you can kind of get what's being talked about. So in this paper, there is a core expression, kind of the central condition of interest. It looks like this. They've got something on the left and it's kind of equal to something on the right. And the expression is going to change a little bit. And I'm obviously going to define what these terms are, so don't get scared of the math yet. We've got a theta in here. We can say that this expression is going to be for many theta. For many theta. Now, don't know what that means yet, right? But we'll get into that. So let's start with D, kind of the most basic thing. D is the data. We could say this is the observed data. So let's just go ahead and define D as observed data. Now that could be anything, the raw phenomenon or phenomena that we are trying to explain. But with these kind of conceptual overviews, I want to use a super real world example just to kind of anchor that mathematics in everyday life. And I think that's a good way to intuitively understand math in general. So I recommend that. Okay, so we're going to have two people and they're at a table and they're having a kind of conversation. And the thing that they are talking about is the issue of morality, okay? Or our kind of sense of what is right and what is wrong, right? So people obviously do this all the time. They argue about fairness, or people accuse others of wrongdoing. People offer, excuses. Sometimes people feel guilt, or people justify actions rather than merely describing them. So in this situation, right, you can use any situation you want, but in this particular one, the observed data here is going to be, we notice that people consistently talk and act as if moral correction is possible, right? So moral is not just this completely fluffy, we don't know what it is. Even if we can't put a kind of put a definite definition on it, people are acting as if the correction is possible, right? Because of the way they talk. So that's what we're observing about a real world situation. Now we're going to go ahead and define what R theta is. And R theta, say mathematically, would be like a family of transformations indexed by theta. So kind of all the different versions or changes you go to do to a system. Science, this might be things like reparameterizations or reductions or just kind of colloquially explanatory lenses, right? It's different ways of explaining away or redescribing the same data. So if this was just any kind of observation you were making in science, this might be all the different ways you try to explain the phenomena that you're actually looking at. But let's go back to the real world morality example and kind of put it through that lens. So each of these transformations, these views, these lenses, right? It's a transformation applied to the same moral phenomena. So again, that thing that we're noticing as we're talking about morality is people, no matter how you might define it, they seem to kind of keep talking as though it definitely exists, right? It's not just this completely fluffy concept. So there's the psychological lens that might help explain that. People might say they only feel guilt. Let's say we're talking about people feeling guilty. They only feel guilt because of conditioning or trauma. Or you could take a cultural lens and you could say, well, they're just following local norms. Or you could take the evolutionary lens and say, well, moral feelings are adaptive instincts. Or maybe there's the preference lens. You could say it's just personal taste. Okay. Now, these are not necessarily wrong per se, but they are attempted reductions, right? You're trying to explain this kind of fuzzy, sometimes hand-wavy issue of morality with something more concrete, right? So transformations in this kind of mathematical sense could be like psychology, culture, evolution, preference, right? They all attempt to redescribe the moral experience that people are talking about. That's what I think. And again, if this was something more in science, like black hole phenomena or something like that, you've got these different angles, these different ways to try to explain the thing that you're observing, which is D. D is observed data, R theta, let's just call them explanations. It's probably the easiest way to think about it, okay? Explanations. Like scientifically call those transformations, though. Like the micropaper, right? Okay, so now we're going to have this S, and we can just kind of define that, kind of running out of room here. Let's just say S. I'm just going to put a dot in the bracket there. And we can call this a structure extractor. So it's a way of extracting what stays the same across transformations. Super common thing to do in science is to look for things that don't change and everything else does. We typically call that invariance, right? So let's go back to that morality example. This would be what survives every reduction attempt. Again, reduction is like the explanation. So all the different explanations you try to give something, right? You're hitting at it, you're hitting morality from psychology, from evolution, from preferences, all these different things. No matter how you hit it, what is it that survives that? So, for example, disagreement behaves as if someone is wrong, right? So these people could be disagreeing about whatever it is. You're right, I'm wrong, but what is right and what is wrong? Like, you only are saying that because you both at some level agree that there's such a thing as wrong, right? Excuses presuppose a violated rule, same kind of idea. Guilt presupposes obligation. Justification presupposes correctness. Different ways of kind of saying that same thing. No matter how you decide to talk about it, no matter what you try to do to explain, right, all your different R thetas, something is invariant there. Something is still surviving. Okay, so this is a kind of, you might call it a moral grammar, not just a moral content, right? So the structure extractor here, okay, this S, right, on the D there, what moral discourse assumes even when people, let's say, deny morality in this example. Okay, so let's say you don't even think morality is real, or it's just completely invented, or however you want to say that. You got all these ways to try to explain it away. It's what moral discourse assumes even when people deny it, right? You're still assuming something. Like if you were trying to convince me that morality is made up, let's say. Okay, well, you're still trying to convince me of something, right? So you're still, in other words, you're still assuming at a deeper level, you're still assuming there's something that's more right and something that's more wrong. Otherwise, why are we even talking? Why are we even debating, right? There's that underlying thing. That's the structure that we're trying to extract from this situation. No matter what you do with your thetas, what is that underlying invariant structure in that system that still perseveres through all of it, okay? And you can imagine this would help make an argument for, let's say, morality truly being objective. Because no matter how you try to explain it, there's still something left over, right? Okay, so let's think about that invariance under transformation. Let's kind of re-express this. Well, actually, let's continue to focus on that. Just remember, D is observed data. You've got your R theta for all the different explanations. We got this real world morality example. So the same structure appears after many representational changes. That's essentially what this expression is saying, right? Because there's the observed data. Here's all the ways you try to explain it. And if you were to extract a structure on that, it would essentially be equal to extracting the structure just on the data itself, right? In other words, for all, again, remember we said for many theta, right? So the same structure appears after many representational changes or many explanations or many transformations, okay? So back to that morality example, even when someone says morality is subjective, okay, this debate up here, you can still say, well, they're still arguing. They still defend themselves. They still accuse others, or they still feel guilt. Okay, so the behavioral structure is invariant, even when the explicit belief changes. Right? It's that idea that you wouldn't be arguing in the first place if you didn't, at some level of abstraction, be agreeing that there's such a thing as right and wrong, or better or worse, right? So the invariance there is moral reasoning keeps reappearing no matter how we try to explain it away. So that's like a real world example in a debate where this expression could be used to essentially define what we're talking about, right? Again, we're observing something. People talk about moral issues. People try to explain it in many different ways, right? Psychology, evolution, whatever. If you were to extract structure from that, you would still be left with structure as if you were just acting on the data alone. It's a way of kind of expressing the invariance. So I hope that makes sense. Okay, now think about the residual structure after the reduction. Let's kind of re-express the fact that it's kind of like a residual. We're saying something is left over there. Okay. And let's kind of do a similar expression, but we're going to go like this. And again, this is in the paper, right? We'll say delta theta D, and we'll actually say that equals the original data minus R theta D, okay? Now, that is what is left over once the reduction has done all the work that it can. So in this case, this guy here, this delta theta, right, we could say that that is the residual data left over after applying the transformation, R theta, to the observed data, right? So we're observing people talking about morality, and they try to explain what morality is. And if you just took the raw data and took the difference between those two, that delta there, that residual, is what's left over after applying a transformation. So it's another kind of way to express the invariance, right? Delta theta right here is going to be indexed by theta because the residual depends on which explanation you tried, okay? So this is still just, we can say this applies for many theta, but we're still looking at one theta at a time. So you come in with one explanation, you apply it to the observed data, and if you take that off of just the data itself, you end up getting a residual, you could say. That's one way to kind of think of that. So morality example, after fully invoking, let's say, psychology, culture, evolution, or preference, you say, well, what's left, right? Let's say the expression, I know what I did, but it was still wrong. That explains my feelings, but not whether I should have acted differently, right? That leftover is the residual. So the residual, right, would be something like, in this real world example, obligation and guilt remain after the causal explanation, right? I know what I did, but it was still wrong, right? You got the causal explanation there, but there's something left over there, right? That leftover is the kind of residual there. Again, it doesn't have to be this real world example. You could talk about something with black holes. You could talk about something, chemistry, whatever it is, right? So the residual structure after reduction, we're basically saying that the residual structure is not just noise, right? So we could say, kind of re-express this, we could say, if you take the structure, remember that structure extractor, and you apply it to the delta theta of the D, right, which is the residual, we're saying that that does not equal 0. And again, for many theta, right? So as you come up with many different explanations, right, the residual that's left over has a structure to it, essentially. The residual is therefore structured rather than random. That's basically what this says right here. The residual is structured rather than random, okay? What survives reduction is not noise, but organized constraint. Okay, so morality example again, the residual is not chaotic or idiosyncratic. So again, this guy here is like, morality is just, psychology is just it's a cultural preference, right? You can't really say there's a real objective morality. And this would be saying, well, if you look at situations like this, the residual is not chaotic or idiosyncratic, right? It has the same form across people. It appears in different cultures. It generates predictable responses, right? Guilt, justification, apology. You see that again and again across different cultures, across different people. Okay, so it's not random. It's not noise. There is a real structure to the residual that's left over. Okay, so you can kind of think of it as like organized constraint, not accidental byproduct. Okay, what remains is not noise. It has a stable shape. By the way, I'm not trying to convince you one side or the other on the morality debate. I'm just using that as an example. And if you wanted to show the invariant structure that there seems to be some objective truth to morality, this might be how you set up the mathematics. Okay. But again, you can use whatever you want. But let's say we continue on that, and if you continue through the paper, you see that now we start to kind of bring in almost what you might call a phenomenology to it, where you don't want to just, this is what I like to do, right? Is you define it mathematically. So let's say your stance was morality is indeed objective. And then you say, okay, I'm thinking of that in terms of invariance, and then you would define that mathematically. But in some sense, that's still a bit arbitrary, right? Because you could take the opposite stance, and then you could just define things mathematically for the opposite stance. And that would be just as justified, right? So you want to kind of bring in a bit of what you know about how nature works, still do it mathematically, but kind of add that or bring that into kind of the framework that you've developed, right? So it's not just an arbitrary mathematical definition, if that makes sense. Okay, so now we're going to think about MDL, which is called minimum description length. And it's kind of a nice way to think about the complexity of a model or an explanation or a thing that you have come up with, right? So information theory, which is where this comes from, provides kind of an epistemic rule for interpreting persistent structure, which is what we're talking about here. We're talking about invariance, right? So under the minimum description length principle, the preferred model minimizes total code length. What does that mean? Well, it's saying that if you have a model, think of it almost like a worldview of something, right? The way you think things work, or literally a scientific model, you prefer the model that minimizes the total description length. So what does that mean? And it is essentially what it sounds like in terms of like basically how much it would take to describe something. Sorry, that's an asterisk. So we're going to say let's say the model the best model. Okay, so think of this as the best model. Okay, is going to be the minimum that we try to find. And then we're going to get these description lengths in here. You're going to have the description length of whatever model you're looking at, plus the description length, you could say, of the data given the model. Now we have to make sure we understand what that means. Okay, so this is essentially penalizing model complexity. Okay, this is like how elaborate your moral explanation is. And I'll reframe this in terms of overfitting and underfitting in a bit, because that might make a bit more sense. But think of it as just model complexity, or a penalty for model complexity. Penalty for model complexity, okay? Probably can't read that, but so that these are both penalties, okay? That's a penalty, that's a penalty. That's for model complexity. So if you have a model and it tries to explain every possible thing at every possible angle, it's basically overfitting the data, you're going to get penalized for that. That doesn't work well in science, right? Because it kind of explains everything and then it doesn't generalize well. You go to put it in a new situation, it no longer makes sense. So you want to penalize model complexity. The other one, which is the description length of the data given the model, this essentially measures unexplained regularity. So how much moral, so forget the model for a second. It's kind of like, the way I like to think about this is kind of in terms of like channel capacity, information theory. So let's say you're sending a message, and if you have the model will tell you essentially how to generate whatever's in the message, right? So I could send the model to someone else, and then they could use that model to generate, let's say, the words that I wanted described, right? Which would be a more compressed way to tell someone a large message, right? Because the model size would obviously be smaller than all the words in the message, right? So there's the model. But the model is not going to get everything, right? So you probably have to send the model plus some data itself, like some of the raw message or something else that tells the model how to do what it needs to do, right? So this right here is basically, once you've applied the model and you got whatever message you can out of it, whatever is left over, that's this. That's the data given the model, okay? So this is like extra stuff. And if you have too much of that extra stuff, there should be a cost to that. Like if I'm sending a message across a channel and maybe you have a really nice compact model, right? Like it's really small. So that's good. But then you have this, because it's so small, it doesn't actually explain that much. And so you have all this extra stuff you got to send over the wire anyway, right? So it's you're trying to get really kind of efficient communication across the channel. That's one way to think about it. Okay, so we say the LDM here, the description length of the data given the models, essentially measures the amount of unexplained regularity. The model captures all the things that are regular in the message, because then it's core pattern that can just be used to generate more and more. But all the extra data, unexplained regularity, has to be accounted for. If you have too much of that, you should be penalized for it, right? So again, argmin, right, you're trying to minimize both of those. You want to get penalized for both of them, right? So if this is the morality example, this guy right here would be how elaborate your moral explanation is, and this guy right here would be how much moral behavior you still have to awkwardly explain away, right? So in other words, I'm going to come in and like, yeah, morality is all about psychology, or it's all about evolution, or I'm going to use all of those explanations, but there's still so much that's unexplained there. You still have to send a lot of kind of residual stuff through the wire, or whatever you want to say, that leftover stuff, in order for the other person to understand what you're really talking about, because what I said about psychology and evolution doesn't really explain the things that we keep observing, about morality, right? It doesn't explain why all these different cultures seem to land on the same thing, for example, right? So your psychology, your evolution, those explanations are kind of insufficient, right? So you should be penalized if you come up with fancy explanations, but you got a bunch of leftover stuff, right? So that's compression and model selection, and minimum description length helps with that. So we know, again, right here, LM, right, it penalizes model complexity. You can think of that as model overfitting, which I said earlier, okay? So the moral example would be like the hyper-rationalized excuse. Okay, so this would be like, okay, explain, why someone thinks something's right or wrong or whatever, right? Well, or more to the point, let's say somebody did something wrong. Okay, and what is kind of an an elaborate explanation or model of why that might be. Well, someone might say, well, given my childhood trauma, my neurochemical state, social pressure, evolutionary instincts, systemic injustice, what else? Situational constraints. My action was actually justified, right? It's like a hyper-rationalized excuse. That's an overly complex model for what happened. If you're explaining something to do with morality, right? Or something to do with right and wrong. It's an excuse. You come up with a super hyper-rationalized excuse, and you can say, well, maybe it's those things. Maybe it is your childhood trauma and your neurochemical state and your social pressure and the evolutionary instincts and the systemic injustice and the situational constraints. Yeah. But does that really justify the action? That's a lot of bloat. And you should be penalized for having that much bloat in your model, because those don't tend to work well just as an epistemic rule. They don't work well in science. They don't work well in decision making. Okay. So the problem with what I just did, that super hyper-rationalized explanation or justification, is that it kind of explains everything once. It generalizes to nothing, right? In other words, it explains everything in this one instance, and then as soon as you go to repurpose it somewhere, it has no use, right? It's like if Einstein, comes up with relativity and it doesn't end up being general, meaning it explains one super specific situation, then you go over to this part of space or this situation or this reference frame and the whole thing falls apart. It's not really that useful. It's definitely not general, right? Any kind of decision-making, epistemic rule, scientific whatever, it can't just explain something once. It's got to generalize to other things. That hyper-rationalized explanation just generalizes to nothing. It grows without bound, right? So you could call that moral overfitting, to use our two people talking about morality example, right? So overfitting is like you're inventing structure just to excuse every case. Okay, and if you do anything in like machine learning or AI, you might think of it like, there's all the data points on your plot, and you've seen the classic example of overfitting, and then you're going to try to fit your line to every possible data thing, right? It'll explain that data super, super well because you basically fit it to every data point. Now you go to a new situation and that model's a piece of crap. It doesn't work because obviously the data is going to look a little bit different and doesn't generalize to the data because the shape is wrong. Okay, this guy here, the description length of the data given the model, that's going to penalize the unexplained regularity, right? This would be like, in the moral example, this would be like moral underfitting. So that's kind of like saying morality is just a preference. Okay, that explanation is pretty cheap. Okay, it's cheap. Well, so it's cheap, which is maybe good because you could say, well, it's got low complexity. Morality is just preference. Seems to have low complexity, right? But it cannot explain persistent disagreement. It cannot explain guilt. It cannot explain justification. So the same structure keeps leaking into the residual, right? That's moral underfitting. Underfitting means you're ignoring structure that keeps reappearing. You're ignoring structure that keeps reappearing. Again, to use that kind of classic kind of statistics ML example, here's all the data, and we're going to use a linear model, or we'll still put a little shape to it, but it doesn't really capture much, right? It captures this, you missed out on all this. You're underfitting, so you're literally ignoring structure in the data. And in the morality example, that's like you're ignoring structure that keeps reappearing. Your model, your explanation is not that great. The best moral explanation is not the one that excuses everything and not the one that dismisses everything, right? It's going to be the one that captures the invariant structure with minimal extra machinery. So in other words, understanding lies between inventing structure and ignoring it. That's kind of the overfitting, underfitting thing, right? So going back to our expression here, right? Apologize for the mess. This guy here, look at the paper, right? Okay. The best model, this guy here, is equal to, or is the one that minimizes the total description length, right? The description length of the model itself, right? So it doesn't overfit by inventing structure or treating noise as signal, right? That'd be something like a conspiracy theory would be another example for that, right? A super elaborate kind of story to try to make the whole thing make sense, right? JFK was murdered, but not just by a nobody. Must have been some big whatever cabal or whatever, I don't know, some big major thing, elaborate, people in power. Like, yeah, maybe, but it's really elaborate. You have to add a lot of things to try to make that make sense. Could be true. There's a lot of model complexity to that conspiracy theory, right? Again, I'm not picking a side on that. I'm just saying that would be an example, right? So the description length of the data left over, and then the other one, right, is the description length of the data left over once the model is known. right? So it doesn't underfit by treating real repeating structure as noise. So for example, saying morality is just preference, right? So you got to get penalized for both of those, and you're trying to find the minimum, keep the model complexity down, keep the residual structure down that's unexplained. If you can do that, then that should be the model you go with. This is really kind of a mathematical re-expression from an information theoretic perspective of something like Occam's razor. Like you're trying to pick the simple theory, but it's not just simple. It's simple in terms of low complexity. It's also simple because it doesn't leave a bunch of stuff unexplained, which tends to complicate things, right? The model itself might seem simple, but if it completely underfits, it misses structure, then that's almost its own type of bloat because it doesn't account for so much. It makes things worse. It makes things, kind of just fuzzy and unknown and hand-wavy. So again, understanding lies between inventing structure and ignoring it. Okay? So that is it. I wasn't planning on these being that long. I'll try to shorten these a bit, but hopefully that made sense. So we kind of had three major kind of core expressions in that micro paper, right? We're defining kind of what invariance was using this kind of structure extractor, just the observed data, indexed, and then the explanations that you kind of do to try to explain what you're observing. You index that by theta because you can have a bunch of them, and then you kind of show the delta, right, from a structure extractor to show that, whatever, there's always kind of a residual left over. There's some type of invariance left over, and the invariance itself is not random noise, it has structure. And then you kind of bring in what I kind of consider like phenomenology almost a bit, where you say, okay, well, look, how does information actually work in nature? Information theory is a really good way to think about that. Minimum description length, which is kind of like the practical, doable version of something like Kolmogorov complexity, but Kolmogorov is kind of like the underlying theory, and then MDL is a way to actually get out of just the abstract concepts and do some calculations with it. Anyways, and it's a good way to just penalize things that are too complicated and penalize things that don't actually explain things that keep persisting and repeating. So just as an epistemic rule, you could argue that there does seem to be one or two things. You can either say, I think there is some objectivity to morality. I don't think it can be explained away just by things like psychology or evolution or cultural preferences, or however you want to say that, because you get a lot of bloat in the epistemic decision. That's, you can go for that moral objectivity version, or you could just say the current explanations don't seem to be that good, or the ones I hear aren't great. If you want to give me a good explanation or model about why maybe morality is not particularly objective and you think it is still kind of preference, ask yourself how you're going to bring down the cost of some of the things, either the model itself because it's bloated, or the fact that you've got all this stuff that keeps reappearing through conversations, through the data that we observe, that you don't seem to be able to explain. Okay, and again, you could don't want to talk about morality, might be relationships, or might be black holes, or might be whatever. Like, this is the beautiful thing about defining something mathematics, is in some sense it won't matter how complex the situation is, because you're not really saying you're right or wrong. You're just saying here's a way to think about it, here's a way to define it. And if you want to take the opposite stance or something, you could also come up with definitions, mathematical, to explain what you're doing, but try to bring some of the phenomena in, just in the sense of, well, here's how you think information works, or here's how you think here's how information is defined. And so if you actually want to make a decision on something in life, you should probably follow rules like this and then go from there. Or you can do this with probability, information theory, probability, right? These are really good kind of ways to ground it in what we seem to know about kind of how nature solves problems, and we obviously need to be aligned with nature. Okay, that's it for this concept summary. I'll try to make the other ones shorter. If you have any questions, just reach out and let me know.